Okay, this is video 2 for the angular momentum unit notes. All right, now this section is going to involve orbits, which might not exactly be uh, really connected with angular momentum, but I think it's connected enough that you'll see, some things that would help out with orbits. All right, so let's begin by trying to calculate the velocity of an orbiting object. So what I want to know is I want to know this linear or tangential velocity. Well, if I were to take a look at a force diagram for the moon or a satellite or anything around in orbit, I would see that there is this radial force that is causing circular motion. So when I study the forces acting on it, I would have a radial force which equals mass times the radial acceleration. Okay, well, the thing that's providing this radial force is gravity. So I got this force due to gravity equals m. Now I have two formulas for radial acceleration, and since I want the linear velocity, I'm going to go with the v squared over r. Now r is going to be the distance from the center of the moon to the center of the earth, or center of the satellite to the center of the earth. All right, gravity has its own formula. It's capital G and the product of the two masses divided by the distance between them squared. Now I can do some algebra. I see that the mass of the satellite, or the moon, cancels out. And I see that this radius cancels out one of those radius. So what we're left with then is the velocity of the object equals g times mass of the Earth or the Sun or whatever's being orbited around, divided by r underneath the square root. So notice that what this means then is that every velocity then has its own discrete radius, where closer objects must orbit faster than objects farther away, and that this velocity then is proportional to 1 over the square root of the radius. All right, now we need to talk then about different radii. And we have some common orbits. And, from the farthest out to the closest one, we have the high Earth orbit, the geostationary, the medium Earth orbit, and the low Earth orbit. All right, so high Earth orbit. All right, so high Earth orbit is defined to be 42,164 kilometers from the center of the Earth. That's 36,000 kilometers from the surface. That's really up there. This is a sweet spot for geosynchronous orbit. So for geosynchronous orbit, what that means then is that it's the same speed as the Earth's spin. What that means is that it's going to stay over the same location of the Earth. So as the Earth spins, so let's say over Ohio, that satellite would always be over Ohio, always. Now it may drift north to south. But predominantly it's going to stay over the same spot. And as you might imagine, that's kind of nice, especially for satellite television, because if you want to have satellite television, you don't want the satellite that's sending the signal to be on the opposite side of the planet. You want it to stay in front of you all the time. This is also why when you have like DirecTV installed at your house, they point the dish south because that that satellite is to the south, but it's in high Earth orbit, so it's in geosynchronous orbit. It stays over the same position. Um, Geostationary is a form of high Earth, so it's like the same distance. This is just it's a high Earth orbit over the equator. And this is where all of our satellites are for, uh, like TV and all that stuff. They're over the equator, and that's why, when they install the dish at your house, they point it to the south because the equator is south of us. And what's nice about this is that it does not drift. So it stays at the same point relative to the ground. You know, so what this does is it makes it very valuable. It's valuable for weather, communications, and monitoring the sun. All right, medium Earth orbit. These are at 26,560 kilometers. Again, that's from the center of the Earth, so that would be 20,200 from the surface. These typically have a period of 12 hours. So that means that they'll go across the same, position on the Earth twice every day. That makes these really nice for GPS. So all of our GPS satellites are in medium Earth orbit. All right, now we come to low Earth orbit. This is where you're going to find the International Space Station. It's in low Earth orbit. Usually these are in what we call sun synchronous orbit. They're roughly at 100 kilometers from the surface. So sun synchronous, what does that mean? You probably heard the song, it's 5 o'clock somewhere. This kind of works the same way. It stays at the same time. Relative to the sun. As an example, there's a satellite that's called Terra, and it's stuck at 10:30 a.m. So basically, it spins in such a way, or it orbits in such a way that as the Earth spins, it stays at the 10:30 a.m. spot. So at one point, it's at 10:30 in Brazil. Then it's at 10:30 in Ecuador. Then it's at 10:30. It stays at 10:30 always. It just kind of it stays locked with the sun so that it stays at that same time. All right, so those are the different orbits. One of the famous scientists who studied orbits of celestial bodies was Kepler, and Kepler created 3 laws for orbit. Kepler's first law states that planets and other satellites will travel in elliptical orbits where the sun or the planet or something is at the focus of one of those ellipses. Now, this drawing here is kind of a little unrealistic. Earth's orbit is a lot more circular than this, but it has a slight ellipse to it. Kepler's second law says that if you draw a line from a planet to the sun, that it sweeps out equal areas in equal time intervals. So, in other words, the area here, this area represents 1 month, going from August to September. This area equals the same area here. So we got the same time, December to January. And this area is the same as this area from April to May. So if we were to go through and calculate those areas, which we'd have to use calculus to do that because it's a curve, we would find that the areas for all of those time intervals are the same. And that is Kepler's second law. Now the third law. The third law says that the square of the orbital period is proportional to the cube of the average distance between the planet and the sun, or between the satellite and the planet. So that's what that is. So what that means then is that t squared must be equal to some constant times r cubed. Change that to a cube. So let's figure that out. All right, well, first off, remember that we figured out when we did the velocities. I'll go with sun. Mass of the sun, mass of the planet. So we had this point right here. And we also did some algebra. Mass of the planet doesn't matter. We got some canceling in the r's. So what we're left with then, g, which is 6.67 times 10 to the -11th, times mass of the sun over r equals v squared. Okay, well, when a planet is in orbit, it's actually pretty close to constant velocity. So that means that this velocity would be like a delta x over delta t. It's in constant velocity. Well, if we think about it, the delta x then is going to be the circumference, if we assume a perfect circle. And the t is going to be the orbital period. Well, circumference is 2 pi times r. So I can plug that in. So what I'm left with then is this. I've got g, mass of the sun, over r equals 4 pi squared r squared over t squared. I could then cross multiply. And I could then solve. So our constant then is this 4 pi squared over g, mass of the sun. And that could be mass of the planet. It could be whatever's getting orbited around. So what this means then, and this is true for all planets, if I were to make a graph of the cube of their distance to their square of the orbital periods, I would see a straight line, where right here would be Mercury, Venus, Earth, Mars. There'd be a jump here, and then we get to Jupiter and the rest of the planets. But if we were to do this, you would see that this graph would occur here. All right, well, that concludes this, this round of notes for this unit.